All right. So we've introduced the atoms and the subatomic particles that make up an atom. We talked about the periodic table of elements, which is again just all the different atoms that exist, all the different types of atoms that exist. Now let's talk about isotopes. Okay, actually, before we jump into isotopes, let me point out a fact about these subatomic particles that's I didn't bring up before, and that is their relative size, right? So we knew protons had a charge of +1, neutrons had a charge of 0, and electrons had a charge of -1. Turns out that there's also something very different about the size or in particular the mass of these particles, okay? And we're measuring mass. One of the things that you'll notice different about what we're talking about here than when, if we're talking about something for lab. In lab, or even if you think about how you weigh yourself, you take the mass of yourself, but you're usually dealing with units that are like pounds, or grams or kilograms. In America, we use pounds. In the science world, we use grams and kilograms. When we're talking about the mass of individual subatomic particles, they're so tiny that we don't use grams or kilograms, because you would be talking about, a millionth of a billionth of a gram or something like that, something inconvenient. So instead what's used are what are called atomic mass units. And really what I want you to know about atomic mass units, or AMUs, is that they're used to measure the mass of something really tiny. Okay? So what we can see comparing the atomic mass unit of these different subatomic particles is that protons and neutrons are about the same size. They both have an atomic mass unit of about 1. All right. And then when we go over to electrons, they are really tiny. That is 2,000 times smaller than a proton or a neutron is the size of an electron. Okay, so just like we talked about how an atom is made up of mostly empty space with a very dense nucleus, just about all the mass of that atom resides in that dense nucleus with the protons and the neutrons. The electrons that are floating around really don't contribute very much to the mass of that atom. Okay, so now we're going to talk about isotopes. What is an isotope? Well, remember, what makes carbon, for example, is the fact that it has 6 protons. If it were to have 7 protons, it wouldn't be carbon anymore, right? But an element, the same element, can have a different number of neutrons. So an isotope is an atom, and it's the same element, but it has a different number of neutrons. Okay? When we talk about the different isotopes of something, we use something called the mass number, symbolized by A. And the mass number is equal to the number of protons plus the number of neutrons. Because remember, that's where the vast majority of the mass of these atoms are. They're in the protons and neutrons. So then we have a special symbol that we use to represent isotopes. One, it sort of goes by this format here. You take the element symbol. So for example, for carbon, that would be C. At the bottom, you use a subscript that indicates the number of protons. So for carbon, that would be 6. And then the mass number is the number of protons and neutrons. And this can change. So for example, for carbon, there's an isotope with a mass number of 12. And there's also an isotope with a mass number of 13. Both of these are carbons. They're just different isotopes. That's what we call them. And what differs between them is the number of neutrons. Okay. So let's sort of look at hydrogen. Hydrogen's another example of an element that has many isotopes. Most elements have a number of different isotopes. Some of them don't. Some of them only have one isotope. Generally speaking, the larger the element, in terms of the larger the atomic number, the more isotopes it'll have. Although that's not always the case, that's broadly speaking how it works. works. Okay, anyways, hydrogen has 3 different isotopes. The most abundant one is, I've never even heard it called protium, but sure, regular old hydrogen, which has 1 proton and no neutrons, right? And remember, the mass number is the sum of the protons and neutrons. So here, let's do mass number. For this hydrogen, that would be 1. Okay. There are 2 other isotopes that aren't quite as abundant, meaning they're more rare, but nonetheless they exist. One of them has 1 neutron, so that would be a mass number of 2, right? 1 plus 1. And the other one, tritium, has a mass number of 3 because it has 2 neutrons. Okay, so notice how that information is summed up in these symbols here. Okay, again, if you were to zoom in on the, I had 1 deuterium and 1 hydrogen, and I zoomed in, what the difference would be is what's going on in the nucleus, right? One of them has no neutrons, the other one has 1 neutron, and the last one has 2. Okay, and so this information about the number of neutrons is really summarized in this mass number here. And you got to do a little subtraction to figure it out, right? If I was just given this and I asked you how many neutrons are in this isotope, you would have to take the mass number of 3 and subtract the number of protons to get the number of neutrons, which in this case would be 2, right? So this is now mass number minus the number of protons equals the number of neutrons. How we figure this out, how we can sort of measure that there are different isotopes, is we have this instrument called a mass spectrometer. We're not going to go too much into how this thing works. It's a little advanced for this course. But the bottom line is you could send, for example, a sample of hydrogen gas into this instrument, and it passes it through this ion beam and then a magnet. The ion beam gives those different isotopes a charge, and then the magnet separates them out. But it does a, what am I trying to say? The degree to which it will bend the path of that ion depends on how big it is. So for example, on one end, you would have your small isotope hitting, and then on the other end, you would have the larger isotope hitting. So, don't worry if you don't understand mass spectrometry. That will come later in your chemistry career. But bottom line is we have an instrument that will actually separate things based on mass. All right, so then the skill that you should be able to do, kind of combining what you learned with this lecture, as well as how to hunt through the periodic table and what we know about the charges of our subatomic particles, is to be able to complete something like this isotope table here, which summarizes a lot of that information. So the first column's filled out. Let's see if we can make sense of it here, right? So first of all, the name, in terms of how we name a particular isotope, is with the regular name hydrogen, and then we stick the mass number on the end there, right? So just like in our symbol, how we had the mass number as a superscript, right? The mass number, remember again, was the number of protons plus the number of neutrons. If we're going to name a particular isotope, this, for example, we would call hydrogen 3, okay? Hydrogen has 1 proton because that's where it is on the periodic table, and it will have 1 electron because it has no charge, okay? And then in this particular case, because the mass number was 3, that means that this isotope had 2 neutrons, all right? So chlorine 35, I'll give you the symbol as well. Let's start filling this out here. So what would be the mass number? Right, that's what 35, when you say chlorine 35, that's what that 35 is the mass number. Okay, remember that this subscript is also the number of protons. And if I didn't know that, I could sort of verify by going back to our periodic table and finding chlorine and seeing that it's at position 17. Okay, since it has no charge, that means that I have an equal number of electrons. And then how am I going to figure out how many neutrons it has? I'm going to take my mass number, right? So mass number minus the number of protons equals the number of neutrons. So 35 minus 17, that brings me to my mass number of 18. Okay. I'll let you guys do the next one on your own. Let's actually skip down to the last one because that one's a little bit tricky in that it has a charge associated with it, a charge of -1. So before we even start doing anything math, it's a good idea to take a step back and think, should this have more protons or should it have more electrons? That's a really easy way to make sure that you're not going to make a mistake. So in this case, first let's figure out how many protons it has. Well, it's fluorine, right? And so fluorine always has the same number of protons or else it wouldn't be fluorine. In this case, again, it's given as that subscript, so it's 9. Now I can figure out how many electrons this ion should have. So if it has a net charge of -1, then I should have more electrons than protons, and I should have 10 electrons, exactly 1 more. What is the mass number? Well, remember the mass number is given both here in my symbol as a superscript as well as in my name. So this would have a mass number of 18. And then how do I find the number of neutrons? Again, I use this same equation where I take my 18, I subtract 9, and that should give me 9 neutrons. Okay?